Take a listen to this. The sound starts off high-pitched, but gets lower-pitched as it moves away from you. The siren isn't changing. This is just a fundamental principle in physics called the Doppler Effect. Sound travels in waves, spreading out from a source. Notice how the circles are all concentric. The distance between each wave crest is the same in every direction. If you were standing anywhere around this car, the pitch you hear, which is really called the frequency, would be exactly the same. The frequency is just how often these wave crests hit your ear. Now let's get the car moving. Let's say it's moving to the right. Now look what's happening. On the right side, in the direction the car is moving, the waves are getting bunched up and compressed. The distance between them is smaller. For a person standing here, these compressed waves will hit their ear more often. That means a higher observed frequency, which he'll hear as a higher pitch. But on the left side behind the car, the waves are getting stretched out. The distance between them is larger. For a person standing here, the sound waves will hit their ear less often, which means a lower observed frequency or a lower pitch. This right here is called the Doppler effect. Let's take a look at the formula. F prime equals F times V plus minus V sub O over V plus minus V sub S. You may have also seen it written as F sub O equals F sub S times V plus minus V sub O over V plus minus V sub S. Now these two formulas are exactly the same, except in the second one, it's a bit clearer that the F on the left side of the formula, F sub O, is equal to the observed frequency. As long as you can remember that F prime equals the observed frequency, you can choose either one. They mean the exact same thing, and you can use whichever one you're more comfortable with. But for the rest of the video, I'm going to use this one. Alright, let's take a look at what each term means. F is the actual frequency, and F prime is the observed frequency, or the frequency that you hear. The V on top is the same as V on the bottom, and that represents the speed of the sound waves. Now, this value might change slightly depending on your textbook, your teacher, or the problem, but the standard value for this is 343 meters per second. V sub O is the speed of the observer, or you in most problems. And lastly, V sub S is the speed of the source of the sound. It's actually supposed to be velocity, but don't worry about that for now. And these are both given to in meters per second, similar to V. And the observed frequency and the actual frequency are in hertz. And there's just one more thing that we have to go over. These plus or minuses. How do you know when to use each one? Sometimes on the bottom here, you might see it written as minus plus, but I always use plus minus, and I'm going to give you a few easy rules to remember that tell you which one to use and when. This is the way that works for my students. Just think about whether the situation should make the observed frequency, F prime, go up or down. These problems are going to be so much easier when you remember these rules. Anytime the source and the observer move apart, the observed frequency will decrease because the wavelength is increasing. And anytime the source and the observer move closer together, the observed frequency will increase because the waves are getting compressed. If the observed frequency should be higher, then you pick the signs that make the fraction larger. And the fraction is larger when the numerator is greater than the denominator. Let's quickly go over why this works. Let's say there's a sound emitted from a siren of 500 Hz, and you're told that the source and the observer are moving closer together. Then you know that the observed frequency will be higher than the actual frequency, so the numerator has to be greater than the denominator. In this example, our numerator 3 is bigger than 2, which makes our observed frequency equal to 750 Hz, which is what we expect because we're told that our two objects are moving closer together, so the observed frequency is higher. Let's see what happens when our numerator is smaller than the denominator. In this example, 2 over 3. This will make the observed frequency sound lower, roughly 333 Hz. So when our numerator is greater than our denominator, we will have a higher observed frequency. And when our numerator is smaller than our denominator, we'll have a lower observed frequency. Back to these rules. When they move farther apart, the numerator will be lower. But when they move closer together, the numerator will be higher. Alright, let's do some practice problems. Number 1. A police car has a siren with a frequency of 500 Hz. If you are standing still and the car drives towards you at 30 meters per second, what frequency do you hear? Let's rewrite the equation on the top. Alright, we're told that the police car has a siren with a frequency of 500 Hz. This right here is the actual frequency, or f. We're told that we're standing still, so the speed of the observer is 0. We're not moving anywhere. So VO is equal to 0 meters per second. And the car drives towards you at 30 meters per second. We're told two really important things. It's driving towards us, so we know right off the bat that the observed frequency will be higher than the real frequency. And the speed of the source is 30 meters per second. They don't give us a V, but unless they give us a different value, we're always going to use 343 meters per second for speed of the sound waves. Alright, we have all the information we need. Let's just plug it into the formula. F prime is equal to 500 Hz times V, which we know is 343 meters per second. And we're going to get to the plus minus right now. VO, we know, is 0. And V sub S is 30. Alright, now let's pick our signs. Up here for the top, we have 0, so it doesn't really matter which one we pick, but it should be plus. And for the numerator to be higher, down here we have to put minus. That equals to 500 Hz times 343 over 313. And you can see that the numerator is higher, so that's why we did plus on the top, minus on the bottom. And I erased the units here just so it's a little bit less overwhelming to look at, but your final answer does need a unit, so we're going to add it back at the end. And when you multiply this out, you get roughly 548 Hertz. And you can see right here that the observed frequency really was higher than the actual frequency, which is what we predicted. So as long as you remember these rules over here, you'll be fine. This was a bit of an easy problem, so hopefully that wasn't too bad for you. And if you did find this a little challenging, don't worry, we're going to do more problems and you should nail it. Alright, let's move on to the next problem. The same police car from the previous problem, with the siren at 500 Hz, has just passed you and is now moving away from you. That's the keyword, moving away from you, at 30 meters per second. So we're given V sub S. Although it's not stated, we are stationary, so V sub O is 0 meters per second because we're not moving. And let's solve. I'm going to make a quick prediction here. Because it's moving away from us, then we know that the observed frequency is going to be lower than the actual frequency. So F prime is going to be less than 500 Hz. That's my prediction. Alright. F prime equals 500 Hz. Again, V is going to equal to 343 meters per second. Plus minus, we're stationary, so it's going to be plus 0 over 343. And we'll get to the sign in a second. V sub S, which is 30. Now, it's moving away from us, so the observed frequency has to be lower than the actual frequency. And that means that our denominator has to be bigger than the numerator. So, instead of subtracting these, we're going to add them. We're left with 500 times 343 over 373. And we're going to get roughly 460 Hertz. Alright, let's move on to the next one. A factory has a stationary alarm with a frequency of 700 Hertz. You are riding a bicycle towards the factory at 10 meters per second. What frequency do you hear? This time, the source is stationary. We're told that here. So we know that V sub S is equal to 0 meters per second. And in this problem, this time it's us who are moving. So the speed of the observer is 10 meters per second. V is always going to be 343. So now we have all the information we need to solve the problem. F prime equals 700, 343. We're going to get to the sign in a second. 10 over 343, 0. So we're moving towards the alarm. The distance between us is decreasing, so we're going to observe a higher frequency. That means that the numerator has to be larger than the denominator. So here we're going to plus, and down here we're going to plus or minus. It doesn't matter because it's 0. So we have 700 times 353 over 343. And we're going to get roughly the 720 Hertz. Okay. A motorcycle with a loud engine, which is the source, and it's at 400 Hz, is traveling at 40 meters per second. You are in a car in front of the motorcycle traveling in the same direction at 25 meters per second. What frequency do you hear from the motorcycle behind you? This problem is a bit different than the other ones that we were doing. In the previous problems, either the source or the observer were stationary while the other one was moving. Here, both are moving. If you remember the two previous rules from earlier, those are still true, but we have to add a clarification. If you remember, we have two possible signs we can use for the numerator or the denominator. We can use either plus or minus for the numerator, and we have the same two options for the denominator. But now we have to figure out which one we're going to use. Before it was much clearer because it was easier to see which one would make the numerator or denominator bigger or smaller, because we were working with 0. So if we were adding 0 in the numerator, then we had to make sure the denominator was smaller. So it was much easier to work with before. But now we actually have to be really specific. Let's take this example. F is equal to 1000 Hz. V sub O, I'm going to say, is equal to 35 meters per second. V sub S is going to be 25 meters per second. And I'm going to tell you that the distance between the observer and the source is shrinking. We know that the distance between us is shrinking, so that means that we'll get a higher observed frequency. F prime is going to be greater than 1000 Hz. So we know that our numerator has to be larger. But there are two ways of doing that. We can have the equation written out like this. For the first one, we can use addition in both the numerator and the denominator. And for the second one, we can add in the numerator and subtract in the denominator. Both of these make our numerator larger than the denominator. We'll get about 1027 Hz here, and we'll get about 1189 Hz here. But how do we know which one is right? They can't both be right. This is why we have to learn a few more rules. When doing a problem where both are moving, you have to ask yourself, are you moving away from the source, or are you moving towards it? If you as the observer are moving towards the source, then use addition in the numerator. But if the observer is moving away from the source, then use subtraction. On the other hand, for the denominator, if the source is moving towards the observer, you use subtraction. But if the source is moving away from the observer, then use addition. So anyway, back to this problem. A motorcycle with a loud engine, which is the source, at 400 Hz, which is our F, is traveling at 40 meters per second. So the source is going at 40 meters per second, which is our V sub S. You are in a car in front of the motorcycle traveling in the same direction at 25 meters per second. So we're told it's in the same direction and at 25 meters per second, which is our V sub O. What frequency do you hear from the motorcycle behind you? We're going to draw out this diagram. Here's the car. It's going this way. And here's the motorcycle. The motorcycle is traveling at 40 meters per second. And we're traveling at 25 meters per second. We can obviously tell here that the distance between us is getting smaller. The motorcycle is behind us and traveling faster than us, so the distance is getting smaller. And when the distance between us gets smaller, then the observed frequency gets higher. So we know that F prime is going to be higher than 400 Hz. If F prime has to be bigger than F, then our numerator has to be larger than the denominator. So we know the observed frequency is going to be greater than 400 Hz. As with every other problem, I'm going to rewrite the formula at the top of the page. And now we can start plugging things in. Let's pick our signs. We know from the problem that the source is traveling towards us, that we, as the observer, are moving away from the source in this direction. So if we're moving away from the source, then in the numerator, we pick subtraction. And for the denominator, if the source is approaching the observer, which the motorcycle is, we pick subtraction also. Now we can start plugging things in. We have F prime equals 400 times 343 in the top and bottom, 25 meters per second for the observer, and 40 meters per second for the source. And we picked subtraction for both. And if we were to simplify this out, we get 400 times 318 over 303. And we can see here that our numerator is bigger than our denominator. And when we solve this out, we get roughly 420 Hz. Alright, that wasn't too bad. Let's do some more practice problems, and hopefully you should get the hang of it. A train horn emits 310 Hz. This here is our F. The train is moving towards you at 30 meters per second, so we're told 2 bits of key information is traveling towards us at 30 meters per second. This is our Vs. And if it's traveling towards us, then the sign in the denominator is going to be minus, but we'll get to that in a second. You're riding a bicycle toward the train at 12 meters per second. So here we're being told that we're going towards the train. The observer is going towards the source, so that's plus in the numerator. And here's our VO. What frequency do you hear? So the net effect here is if this was the train and this was the observer, the train is going this way and the observer is going this way. The distance between us is shrinking. So we know that the observed frequency is going to be higher than the actual frequency. The observed frequency is going to be higher than 310 Hz. Before we even start the problem, we have a few questions we can ask ourselves. Is the distance between us getting smaller or larger? From this diagram here, we can see that the distance between us is getting smaller. And that means a higher f prime. Are you moving towards the source or away from it? We're moving towards the source. We're told that in the problem. Which means that the numerator is going to be plus. And is the source moving towards or away from us? It's moving towards us. And that means that we're going to pick subtraction in the denominator. And now we can start doing the problem. F prime is equal to 310 times 343, and we picked plus 12. And in the bottom, we have 343 minus 30. And now when we solve, we get 310 times 355 over 313. So our numerator is greater than the denominator, which means that we are going to get a higher observed frequency. So we can already tell that our prediction is accurate, and we picked the right signs for this problem. And when you solve this out, you're going to get roughly 352 Hz. And there we go. We said that our observed frequency is going to be higher than 310 Hz, and we got 352. Let's move on. A car horn emits 540 Hz. That here is our F. The car is ahead of you and moving away. That's important. And it's traveling at 20 meters per second. So this right here is our Vs. And if it's moving away, then it's going to be plus in the denominator. You are walking in the same direction at 5 meters per second. So you're walking towards the car. And if you're moving towards it, you pick plus in the numerator. And this here is our VO. Given that V is always 343 meters per second, unless otherwise specified, that's the value that we're going to use. And we can answer these questions on the bottom. Is the distance between us getting larger or smaller? Let's see. We're going to draw out a little diagram. Here's the car, and here's us. The car is ahead of us, and it's moving away. So it's going in this direction over here at 20 meters per second. We're walking in the same direction the car is moving at 5 meters per second. So is the distance between us getting larger or smaller? The car's ahead of us and it's going much faster. The distance between us is increasing. And if you think about it, if you and your friend were running and your friend is much faster and much farther away from you, then the distance between you grows. So we know that the distance is increasing, and that means a lower f prime. Now we can plug everything in. We have f prime is equal to 540 multiplied by 343, and we picked the plus sign over here, plus 5 over 343. We also picked the plus sign for the denominator, plus 20. We can already tell that the denominator is higher than the numerator, which means that we are going to get a lower observed frequency. And if you'd rewrite this, you get 540 times 348 over 363. You'd roughly get 518 Hz, which is lower than 540. So that means our prediction is correct, and we pick the correct signs. And before even attempting this problem, you can answer these questions. Is the distance between you getting larger or smaller? We know that the distance is increasing, so it's getting larger. Are you moving towards the source? Yes. And if we're moving towards the source, then we know that the numerator is going to be plus. Is the source moving towards you? Yes. Which means that the denominator is also going to be plus. And then we just plug everything into the formula. An ambulance siren emits 700 hertz, which is the F. The ambulance is behind you and gaining on you. So if it's gaining on us, then we know that the distance is decreasing. And it's traveling at 36 meters per second, which is our V sub S. You're driving forward at 32 meters per second, which is our V sub O. So let's draw this out. Here's our ambulance, and here's the observer. The ambulance is going 36 meters per second, while we're going 32 meters per second. We're told that the ambulance is gaining on us, which means that the distance is getting smaller. If something was behind us and going at a faster speed than us, then it's going to get closer and closer. Even if it didn't tell us this part over here, we could figure it out on our own. So the distance is decreasing. And when distance decreases, the observed frequency increases. So we can predict that the observed frequency, or f prime, is going to be greater than 700 hertz. Okay, now if we were to plug everything into the formula, we have to ask ourselves 3 questions. Is it getting closer or farther? Are we moving towards or away from the ambulance? We're trying to get away from it, so if we're moving away from it, we pick minus in the numerator. Is the ambulance moving towards or away from us? It's moving towards us, so in the denominator, we're going to pick minus. And we have our signs. Now when we plug it in, we have f prime is equal to 700 times, we already know our signs, is going to be subtraction in the numerator and subtraction in the denominator. V of 343, VO is 32, and V sub S is 36. We're going to get 700 times 311 over 307. And we're going to get a frequency of around 709 hertz, which lines up with our prediction right here. All you have to do is remember the simple rules. And when you get to a problem, don't rush. Just think logically. Should the observed frequency be higher than the actual frequency, or should it be lower than the actual frequency? Is the observer moving towards the source? And is the source moving towards the observer? And you pick your signs from there. The more problems you do, the easier this is going to get. So just keep practicing. As always, thank you for watching, and I'll see you in the next one.